Given the river width and the number of lanes of vehicles with other configurations, we can draw the bridge geometry and also analyze the loads. Welcome to Bridge Engineering. We are to analyze the geometry and loading of a simple span pre-stressed bridge which spans across a river of 50 feet width. The bridge shall have 2 lanes and 5 feet shoulders on either side. We are to use deck thickness of 7 inches, and there are 32-inch F-shaped concrete barriers on both sides. We are to use AASHTO I girders. We start with the bridge geometry, that is, for the bridge span. The bridge traverses a 50-feet waterway, and accounting for the abutments, we add 5% on either side, thus having 50 plus twice of 0.05 of 50, which gives the span or length of the bridge as 55 feet. Next is to determine the depth. The girder depth can be found using AASHTO tables. The relevant descriptions are: first, the bridge is pre-stressed, so the table we use is that with pre-stressed concrete. The problem also states that the girders are AASHTO I girders, so we look for precast I beams, where we are to use the function 0.045 of L. So plug the length of 55 feet into the equation to have the girder depth of 2.475 feet, which is equivalent to 29.7 inches, again rounded off to 30. Having known the girder depth, we check the AASHTO I girders. AASHTO standardized their I girders into 6 types, and knowing the depth of 30 inches, we can identify the type of girder taking the nearest as 36 inches, and that is AASHTO I girder type 2. To summarize the superstructure's depth, the girder is 36 inches. Add 1 inch haunch and 7 inches deck. Then, the integrated wearing surface is half an inch, and the future wearing surface is 2.5 inches. The superstructure's depth is then 47 inches. Knowing the depth, we can determine the girder spacing using the spacing to depth ratio of 1.5. The girder spacing is 1.5 of 47 inches, which gives 70.5 inches, or that is 5.875 feet. We then compute for the number of girders required. This is computed as the bridge width divided by the girder spacing, then add 1. That is the summation of 5, 24, and 5 all over 5.875, which results to 6.787 rounded to 7 pieces. Let's then refine the spacing. The bridge has 2 lanes of 12 feet each. Then 5 feet shoulders are on either side. The girder spacing is then 34 divided by 6 base, which is then 5.6667 feet, or that is 68 inches. Learning about the bridge's geometry, we can then compute the loadings. Taking the girder, the deck is connected by a haunch. Then on top of the deck is the wearing surface. There is also stay-in-place forms which add to the dead load. In order to compute for the loading of each girder, the load is solved from the tributary width, which we have cleared previously as 68 inches for the interior beams. Now let's analyze the loads. PW is the load of the wearing surface. The computation requires the unit weight of the material used, and wearing surface usually is asphalt, having the unit weight of 0.14 kip per cubic feet. dW is computed as the thickness of the wearing surface multiplied by the tributary width times the unit weight of asphalt. In numerics, dW is 3 inches converted to feet times the tributary of 68 inches, also converted into feet, then multiply the unit weight of 0.14 kip per cubic feet. dW is simplified as 0.1983 kip per foot. The next component is deck, which is included in DC. The deck uses concrete and the unit weight is 0.145 kip per cubic feet. Similar with the wearing surface, this is computed as thickness times the tributary width with the unit weight of the material. DC deck is then 7 inches transformed into feet times 68 inches into feet, then 0.145 kip per cubic feet. DC of the deck is 0.4793 kip per foot. There is also hunch, which is also concrete like the deck, so the unit weight is that of concrete. The hunch doesn't use the tributary width, but only the width of the top flange. To determine the width of the top flange, let's check the properties of the eye girders again. The girder used for the bridge is type 2, and the width of the top flange is denoted as W2, where W2 of type 2 is shown as 12 inches. DC of hunch is then computed as 1 inch thickness converted into feet, then the top flange width of 12 inches also converted into feet, then multiply the unit weight of concrete, which is 0.145 kip per cubic feet. DC of hunch is computed as 0.0121 kip per foot. Another component in the dead load computation is the stay-in-place form, the unit weight of which is 0.005 kip per square foot. The length of the form is the tributary width less the width of the top flange. So the computation becomes the tributary width of 68 less the top flange width of 12 inches. This is converted into feet. Then multiply the unit weight of 0.005 kip per square foot. This is then simplified as 0.0233 kip per foot. The last component from the cross-section is the girder, where the dead load is taken from the properties of the eye girder. Type 2 girder shows the weight of 384 pounds per foot, which is then converted into 0.384 kip per foot. Although not illustrated, the problem also discusses concrete barriers on either side of the bridge. The barriers are 32 inches F-shape, and using the table, we see the unit weight is 460 pounds per foot, taken as 0.46 kip per foot. Since there are more than 6 girders for the bridge, the 3 nearest girders to the barrier shall support the dead load. Thus, the unit weight is divided among the 3 girders, giving 0.153 kg per foot for DC barrier. To summarize the loads, dW was computed earlier as 0.1983 kg per foot along the stretch of the bridge. So the maximum shear is computed as the uniform load times the length upon 2. This is used for simple spans. Placing the values, the shear is computed as 0.1983 times 55 all over 2, which gives 5.45325 kips. For the maximum moment, the function is WL squared upon 8 for simple spans. The moment due to dW is then 0.1983 times the square of 55 upon 8, which results to 74.9822 kip foot. Solving for shear and moment due to DC, we take the summation of all the dead loads of the components. Those are coming from the deck, hunch, stay-in-place forms, girder, the barriers. Also add DC for miscellaneous materials such as utilities and bridge railings. This is taken as 0.020 kip per foot. The total DC is 1.0717 kips per foot for the two interior girders after the exterior end. The maximum shear is then solved as 1.0717 times 55 upon 2, which gives 29.47175 kips. The maximum moment is then computed as 1.0717 times the square of 55 over 8, resulting to 405.2366 kip foot.